I'm Dean Chester. I'm the simulation and modelling lead at Cornelis Networks, and I'm building our models of our next generation fabrics going forward. I'm going to give you a quick company overview of where we are, where we came from, and where we're kind of going. A simulation overview of how we're modelling and simulating our CM5000 product lines and future generations past that. I'm going to give a brief overview of some of the features that we're currently really experimenting with to aid researchers and scientists to get the best deployments and the best configurations for their available budgets. And then, yeah, that's pretty much it. So we spun out of Intel in about 2020, about 3 years ago. We bought out the IP from Cray and QLogic, so we have Ares Heritage and QLogic's InfiniBand 440 gigabits per second technology behind us, and then we've got the OmniPath 100. Going forward, we're going to look towards like CXL technologies and network-based computation in future generations. The start of the company, they were keen on redesigning our software infrastructure to support generations going forward. So there was a big push to untie PSM2 from our software stack and incorporate libfabrics. So that's been done over the past 2 years. That's going to be our software stack going forward. We're going to have our OPX provider that will do all your low-level transport layer inside of your machines. The simulator we use is built on top of the structural simulation toolkit from Sandia National Labs. This simulation toolkit was chosen because it's really, really flexible. So the toolkit itself is a parallel discrete event simulation framework that parallelizes really well. So you can construct multiple components within your simulation, and then you can completely parallelize that as far as you can. So you can push all your switches to single cores or what have you, which means we have this really, really scalable simulator for doing system level simulations. What's really nice is they've provided some functionality already for doing simulations. So they've got this Ember motif engine that replicates applications and workflows from primarily DOE multiphysics applications. They've built like an MPI SHMEM layer on top of that called Hermes. And then they've built network interfaces with Firefly, and then they've got a completely customizable switch and routing module on top of that. We are currently, with Sandia, redesigning the top 3 elements to fit more into our libfabric approach to support both other vendors and ourselves going forward, so we can have a consistent base with our models. This work's really a push from the DOE and other US government agencies who really want to see SST tightly combined into other like procurement processes where they can see models and predictions, and they've got confidence because they funded some of the development work behind that, so they can see that the models that the vendors are then giving them are going to be accurate. This started off during my PhD, where I started to validate OmniPath, where we ran an OSU bandwidth benchmark. This benchmark sends lots of messages and then waits for the receives before doing it, which stresses an underlying part of the network hardware that a traditional latency or bandwidth benchmark wouldn't. So if you just take a peak point-to-point, you don't stress as much of the memory subsystem and lower parts of the software stack as you'd expect. This tells us that the model we started with is really, really accurate and is a good representation of where we want to be heading and using for future projections. We then look towards doing all reducers, which are quite complicated operations to do because there's lots of software overhead, and for 28 ports per node, processors per node, we ended up with about a 10% error, which is really good. When I started at Cornelis, we improved that further to about 8 when we went away and timed some of the RTL of our old hardware and plugged that into our model. So going forward, Our new generational features are going to support telemetry-based adaptive routing, new topology support for megaflies and dragonflies, and enhanced congestion control and QoS. So, as I was saying, SST provides this really flexible framework where we can rewrite modules and put in custom IP behind it that we can then go away and validate. That gives us a base where we can change the different parts of the stack and evaluate all the different kind of conditions, because this parameter space is very large, especially if you take like a system that doesn't have a fixed workload on it, you know, like a university-wide machine might have physics, chemistry, and like HPC research on it as well. So, yeah. Then as part of what we're trying to do, we're trying to tie that into future product development, right? So we want to design and assess trade-offs before we start building our ASIC, but we also want to start using this, what we already have built, to be able to design better solutions with our customers. So we want to sit down with our customers, understand what their workloads look like, plug these in so we can try and tune and deliver a better experience when hardware hits the floor, where you have fewer software errors involved in that kind of process. And then we want to tie that back in, so we're currently building into our software infrastructure the ability to pull out information that we can feed back into the simulations to diagnose any issues where you might have routing tables or collisions inside of paths inside of the network. So our routing pipeline is cycle accurate, and we verified that against the RTL. With a single pipeline, we support both adaptive and dispersive routing, and it supports a wide variety of topologies. The key ones we are targeting again are dragonfly factories and megaflies, but we have this route pipe that we can configure and wire up in any particular fashion. So one of the architects took away the simulation configurations we generated, tuned them to run in their design verification environment for when you have to validate how an ASIC works, and proved that the paths that he'd chosen matched what our model was suggesting for both adaptive routing and dispersive routing, which is fantastic because there's this spec and everybody's got different interpretations, so it's really nice to see that level of validation going on behind the scenes. So as we think about like deploying the fabrics, we have to currently deploy a fabric kind of looks a bit like this apparently, as one of my solution architects told me. You bid the design, you generate a cable map, and then you put the hardware in and it churns out a configuration. Now let's try to plug SST into all of these bits. So currently you can now generate the proposed design, feed that into SST, run a simulation, change some parameters in your software stack, such as adaptive routing and thresholds, QoS, and then you can see how it improves, see how it doesn't improve. That should give us a fairly good baseline for when the hardware hits the floor, that we think your configuration for your fabric manager should be this, and then we should be able to plug it together. So in terms of simulations exploration, some of our work's been funded by the Department of Energy in the US. And one of the key interesting points is, where's the transition point should you swap between the factory, the dragonfly, and the megafly? And we found this 13,824 point interesting, because you can get a full bisection factory with our proposed architecture. You can get a reasonably priced dragonfly, and you can get a megafly. So we are beginning to work with them on building some scenarios that they actually see on their hardware so they can evaluate these design decisions before they put them in for procurement. At a higher level, we can also look at what can we do to optimize the cost within a topology. So if you take, for example, that a dragonfly has 2 links per terminal link inside of a group, what happens if we reduce this down to one link to reduce a cable cost and increase the number of ports available on the switch, so you could add another terminal? Well, we found actually if we did that, the latency between most of the points, even when it became heavily congested, under a steady network load. Didn't really create a concernable difference. You know, you're going from 102% down to 104% down to like 102, which isn't significant at all, and it's something to consider in a solution design. Then we can start doing the application analysis on top of that. So, as I said, we're working with the DOE, so we've got these motifs that represent different style workloads that they see on an application. So we've written a replication of their job scheduler, so we can schedule a random number of jobs and allocate them around the system and see how they interact with different routing parameters. We used random seed 99 as our baseline to just generate some jobs, and we generated 549 jobs from 4 nodes up to 64 nodes, because these are what you'd typically see on a small scale system, and then you can just see how they're going to interact and what's going to happen. The idea of doing it with the scaled approach is that domain scientists typically like to do parameter sweeps where they might schedule a batch of jobs that are all the same kind of run size but have slightly different parameter tweaks, you know, if you have a different starting temperature in a simulation or what have you. So we were able to generate this. These graphs show us how, for the different node allocations, the variance across the run times that we're going to projectively see. And we can see that in the cases where they are all against each other, the adaptive doesn't create the best solution compared to the dispersive routing that we're proposing. There are cases though where the adaptive routing reduces the variability in the runs, which is the important thing, because you know, if you've got a user there at the trying to simulate a job and they're going, I'm just going to request the max wall time all the time because my job can take anywhere between an hour and 4, then that doesn't help you. So being able to understand what the variability is between all these runs, it's really useful, because then you can improve the efficiency and the throughput of your queue. So yeah, the design space for modeling and for building a large-scale fabric is really, really complicated. Having a framework like SST allows us to like decrease this parameter space and explore things that are purely solution and application based. And it also allows us to start thinking about how to tune the networks prior to the deployments. As we go forward, we've got CN5000 coming out in the near future. Then we're going up to 800 gigs and 1.6 terabytes coming soon. So if you've got any questions, come have a conversation. There's 3 of us from Cornelis, me, Patrick, and Alistair. Otherwise, thanks.